Hello everybody, this is Mr. Ainsworth. We're going to get into a topic in calculus called related rates. This is chapter 2, section 6. And what we want to basically do is go over how to find how fast something is changing as it's related to another rate or speed which is also changing, hence the name related rates. So we're going to go through a variety of problems here, starting with something simple and graduating to more complicated ones, showing you how to find basically how fast something is changing. How fast is something changing as it relates to another rate or speed which is also changing. To do that, we're going to write out any formulas and information. Basically, that's the given. And we're going to figure out what we have to find. We're also going to find out a primary equation that obviously relates back to something we already know. Typically, it's from geometry. Okay, typically, but not always. Sometimes it's pre-calculus. We're going to differentiate that equation in respect to time to solve for whatever relate we're working with, and to do that, we're going to have to do some substitution and simplification. All right, that's a lot to do. So let's get started with an example here, and let's find how to deal with what are called related rates. The first problem goes like this: the radius of a circle is increasing. Okay, the radius is increasing here at a rate of 3 centimeters per second. We're given that. So what I like to do as I read a problem here is I like to interpret it and write down what it means in calculus notation. If the radius is changing at 3 centimeters for every second, we interpret that as a change in radius over time. And in calculus notation, that's dr dt. The change in radius, dr, over time, dt. dr actually is a change in the radius, in this case in centimeters, and in respect to time we're talking about per second here. So the change in radius over time is 3 centimeters for every second in this case. That's what's given in the problem. What we want to do is we want to find how fast, right here, how fast the circumference is changing in respect to time. Okay, how fast the circumference, we'll use capital C for that. How fast is that changing over time? We call that dc dt. All right, and what is that value? Well, whenever they say how fast, or ask you to find out how fast something is changing, it's the rate of change over time, and typically it's per second, or it could be per any unit time, but in this case it's per second. So how fast is that changing as the radius is changing? The circumference is obviously related to the radius of the circle, and so as the radius changes, the circumference changes. Okay, the circumference, as you recall, is the distance around the circle. The question is, how fast is that changing over time, which we call in calculus dc dt, the change in radius, circumference over time. So dc dt represents our rate of the circumference as it changes over time. You know, what is that in this case, if we know that the radius is changing 3 centimeters for every second? Well, to figure that out, we need an equation that relates the two. That's called the primary equation in this situation. And in this case, the circumference is related to the radius by c equals 2 pi r. Okay? In any situation, you're always going to have an equation that relates the quantities that are changing over time. Once you find that equation, what you do is you differentiate it in respect to time. You always differentiate. All right, the primary equation in respect to time. The primary, because sometimes there's more than one, so I say primary in this case. Primary equation in respect, all right, to time, because the rate is, you know, how fast something is changing over time. So how do we write that? We're talking about d something dt, ddt. So instead of taking d dx like we typically do when we have an equation, a function y in terms of x, we're going to take a derivative in respect to time. Okay, again, let me underline that, in respect to time. All the related rate problems are in respect to time, because it's a speed, it's a rate. Okay, so here we go. We're going to take c is equal to 2 pi r and we're going to differentiate both sides in respect to time. So I want to differentiate the circumference in respect to time, and I want to differentiate the right side as well, the 2 pi r. Okay, now the derivative of the circumference in respect to time is called dc dt. Okay, that's the rate of change of the circumference over time. That's how fast the circumference is changing per second in this case. Well, when you differentiate this right here, remember r, the radius, is a function of time. The derivative of this using the power rule is 2 pi, or basically you can think of it as 2 pi times the derivative, okay, of the radius in respect to time. So 2 pi times the derivative of r in respect to time is dr dt. So I get 2 pi dr dt. And you remember that 2 pi is just a constant. You can pull it out, this portion right here. You can think of it two ways. You can just think of a simple power rule, or you can pull the constant out in front of the derivative and just focus in on the radius. And so the derivative of the radius in respect to time, well, that's dr dt. Okay, so now I have the change in circumference over time is equal to 2 pi times the change in radius per unit time. Well, I know that it's 3 centimeters for every second. So what I'm going to do is I'm going to substitute that in. So I get 2 pi times 3 centimeters for every second. That gives me 6 pi centimeters per second, which is how fast the circumference is changing over time. Okay? Now that's a constant, and that's why the title of this example right here is how rates of change are constant sometimes. 6 pi, as you know, is a constant. It's almost 20. Because pi is a little over 3.14, or it's about 3.14, so multiply that by 6, you're close to 20. So the circumference is changing at a rate of almost 20 centimeters per second as the radius is changing 3 centimeters per second. Hence the name related rates. The speed of the circumference, or how fast it's changing over time, is related to the rate of the radius as it changes over time. That's where the whole title of the lesson comes from. One rate is related to the other rate. The circumference, the distance around it, changes and increases as the radius increases. Now sometimes rates of change are not constant, like this last example. 6 pi is constant. Okay, well, it's not always that case. Sometimes they change as something else changes. So let's see how the rates of change are changing actually as things change. And if that's not confusing enough, let's just try it. Okay? So here we go. We always want to write down the given in the situation here. The radius of a circle is increasing. That's a positive number right here of 3 centimeters per second. And as I said before, that's the change in radius over time, written as dr dt. And that's going to be equal to 3 centimeters per second. And that's a positive value because it's increasing. Remember that. If things are decreasing, we're going to write that as a negative. And if things are increasing, it's a positive. This time, though, we want to find how fast the area is changing over time when the radius is exactly 5 centimeters long. Well, if I want to figure out how fast the area is changing, that's dA dt. That's the change in area over time. Change, okay, in area over time. You see, as the circle gets bigger and bigger and bigger, the area inside of it increases. But how fast is it changing when the radius is exactly 5 centimeters long? Which only happens, an instantaneous moment in time. Exactly what is it? Because after that, it changes. It's something different. Okay, so we want to find the change in area over time when the radius is exactly 5 centimeters long. What is this value? What is the rate of change of the area over time when the radius is exactly 5 centimeters? Okay, at that moment in time, how fast is the area changing as the radius is changing 3 centimeters every second? Okay, so now what I'm going to do is I'm going to pull in an equation that you know about a circle. And I know that the area in a circle is equal to pi times the radius squared. Okay, well, let's differentiate that equation in respect to time to generate this derivative, dA dt. So differentiating, okay, we want to differentiate in respect to time here. We take the derivative in respect to time on both sides. Keep it in mind that both area and the radius are both functions of time. So the derivative of the area in respect to time is dA dt. It's better to use that notation than A prime. Okay, so the derivative of the area in respect to time is dA dt. Pi is just a constant, so you really just have to focus on the differentiating r squared in respect to time. Now remember, r is a function of time, so you want to use a chain rule here. You differentiate the outer function, the squaring function, using the power rule, and then take the derivative of the inside function r in respect to time. So we have a chain rule going on here. Remember that r is a function of time, so we have a function being squared. And whenever that happens, well, you have a chain rule. Okay, so here we go. We have the derivative of, or dA dt, the change in area over time, is equal to pi times, okay, derivative of r squared would be 2r, times the derivative of r in respect to time, that's called dr dt. So once again, there's a chain rule from here all the way to here in this step. Let me highlight. So this portion right here is this portion here. Again, using the chain rule. Well, how fast is the area changing? Well, I need to know the moment in time when the radius is 5 centimeters. So I want to take 5. I want to substitute 5 centimeters, okay, in for the radius. I want to take 3 centimeters and substitute it in for dr dt, and then figure out, what I have. So let's go do that. I've got pi times 2 times the radius, which is 5 centimeters, put the units in there, times dr dt, which is 3 centimeters for every second. If you multiply all this out, you get 2 times 5 or 10, times 3 is 30, times pi is 30 pi. Centimeters times centimeters is square centimeters for every second. Now let's see if this makes sense. Now we're trying to solve for the change in area over time, and we know that area is always expressed in square units. So when I ask you to find how fast the area is changing, I'm talking about how many square centimeters per second is it changing. So my answer makes sense unit-wise, because area is always in square units. And now this only happens when the radius is exactly 5. When it's 6 centimeters, well, it's going to be different. It's going to be bigger. So the bigger the radius, the faster the area is changing per unit time. The rate of change of the area of the circle depends on not only the rate of change of the radius, but it also depends on the exact value of the radius at that moment in time. These are called instantaneous rates of change. Let's write that down. Okay? Instantaneous rates of change. Okay? The change in the area over time is about 30 pi, is equal to 30 pi square centimeters per second, which is approximately about 100, a little over 100 probably, because 30 times 3.4 is close to that, square centimeters per second. At the moment when the radius is 5 centimeters. After that, well, it changes. It's bigger. Okay? Now this all takes getting used to, so let's go ahead and take a look at another one here and see how we apply it to these situations. In this case, we have a rectangle now that's increasing. Again, that's a positive value at the rate of 3 centimeters per second, or one side of the rectangle is increasing. Which side, we'll have to figure that out in a minute. So one side is increasing, that's a positive value, 3 centimeters per second. The other side is decreasing at a rate of 4 centimeters per second. So this is negative. Okay, why? Because it's decreasing there. The question is, right here, how fast is the area changing? When the increasing side, we'll determine that in a minute, is exactly 12 centimeters long, and the decreasing side is 10 centimeters long. What's going on there? Okay, now to write down the given and interpret it, we need a diagram here. So in this case, I'm going to draw a picture over here. We're going to draw a diagram. So let's go ahead and do that. Let's draw a rectangle here. And let's label the sides with common notation. We usually call the width W and the length L. Okay? And what we need to do is decide which side's increasing and which one's decreasing to solve the problem. Now it doesn't matter which. We just have to make a decision. So let's assume that the width is increasing. So the increasing side is W. Okay? And the decreasing side, well, let's call that L, the length. So the length is going to go longer. It's going to get longer here. It's going to go up. And the decreasing side, what's going to be shorter because it's decreasing. So over time, the rectangle, let's put it in red here, is going to look like this over time. Because like I said, the width is going to be increasing and the length is going to be decreasing. So over time, it's going to be tall and narrow versus wide and narrow vertically. Okay, so the width is going to be the increasing variable, and the length is going to be the decreasing variable, and their rates are given in the problem respectively here. So here we go. We're given that we determined, or we decided that since the width is increasing, the change in the width over time, call it dW dt, is equal to 3 centimeters per second, and that's positive, so I'm going to put a plus there. Just to make sure that you understand that since it's an increasing value, it's positive rate. And since the length is decreasing, the change in the length over time, call it dL dt, is equal to negative 4 centimeters per second. Why? Because it's decreasing. Okay, so what we did is we draw a little diagram here. We determined some variables that we're using in the situation, and we're interpreting them according to the problem. And what we need to do is we need to find something, of course, and that's right here, how fast the area is changing. That's the change in area over time, call it dA dt, when the increasing side, W here, the increasing side is W, and the decreasing side right here, that's L, is 10 centimeters long. So the way we write that in calculus notation is dA dt. We want to know what that equals when the width is exactly 12 centimeters long right here, and the length is exactly 10 centimeters long. What is that value? Okay, this vertical line means evaluate. We want to evaluate the derivative, which represents the change in area over time, when the width is exactly 12 centimeters and the length is exactly 10. Well, to do that, we need an equation, obviously. And the obvious equation that deals with area for a rectangle is length times width. Area is always equal to length times width for a rectangle. Okay? So what we need to do now is differentiate the primary equation in respect to time. So we start off with saying, okay, A is equal to L times W, and that's a product. Okay? Now keep that in mind. If it's a product, well, we're probably going to have to use the product rule. Thank God we learned to do that a couple sections ago. So I want to differentiate the left side. When I differentiate the area in respect to time, I get dA dt. And when I differentiate the right side, I have to use the product rule. Derivative, take the first times the derivative of the second plus the second times the derivative of the first. And what do I get? I get L times dW dt, the derivative of the width in respect to time, plus the width times the derivative of the length in respect to time. Okay, and now after you differentiate, you substitute your values in. Okay, you always differentiate and then substitute values in. Well, the length is 10, so I want to substitute in 10 centimeters here for the length. Multiply that by the change in the width over time, and that's 3 centimeters per second. Plus the width, when it's exactly 12 centimeters, times the change in length of the length, change in the length over time, and that's, well, it's decreasing, so it's negative 4 centimeters per second. Okay, and then we got 30 here, and we got a minus 48 here. That's going to give us a negative 18 square centimeters per second. And then you got to ask yourself, what in the world does this mean? if the change in area over time is negative 18 square centimeters per second, that means it's decreasing, indicated by the negative sign here. So it's a decreasing rate. Okay, let's write that down. It's a decreasing rate indicated by the negative sign. If it was positive, I would say it's increasing, but it's negative, which means that it's decreasing. And that should make sense too, because over time it's going to look like this. Let me draw another picture later on in the situation. It's probably going to be, well, let me change, I got the wrong tool here. I want to get my rectangle tool. Over time it's going to be super long and narrow, and then it's going to be really, really thin, really, really tall, but really, really thin. And so the area is changing. It goes from black to red to green here. You can see how it's getting more long and narrow, and the arrow is decreasing, indicated by the negative sign on the derivative here. So keep that in mind. Positive rates or increasing rates are always positive. Decreasing rates are always negative. Okay, and also remember too that this is a video here, and you can always go back and review this again, listen to my explanation again, talk about it with your friends, other teachers, what have you. Okay? And then of course try your homework problems, because each one's different, and to get good at this subject here you need to solve a lot of problems. Okay? That's why I go over a lot of examples. Okay, now this is a tough one here, but an interesting one, so let's go ahead and go through it together. And it's pretty cool. Okay? And here we have a lighthouse that's located on a tiny island 3 kilometers north of point A. So we're going to assume that this up here is to the north, and this is to the east, and of course, down here is to the south, and down here is to the west. So never eat shredded wheat, north, east, south, west. Okay, so you've got a shoreline here. You got point A here. A lighthouse is located on a tiny island 3 kilometers north of point A. So this is 3 kilometers here. The lighthouse is here, of course. That's L for lighthouse. L is lighthouse here. Okay, and it's 3 kilometers from point A, and this is the shoreline. Right here in the yellow, that's the shoreline. Okay, the lighthouse lamp rotates at 5 revolutions per minute. 5 revolutions. That means full turn per minute. So 5 full turns per minute. How fast is the illuminated spot on the shoreline moving along the shoreline when it's exactly 6 kilometers from point A? Okay, so what's happening here is that it's rotating in, we'll say, a counterclockwise direction here, and the spotlight starts here at point A, but then it moves this direction, like this, and then the question is how fast, again, how fast is illuminated spot moving? Well, I stands for illuminated spot. It's right here, let's say. And that's obviously a certain distance from point A right here, which is indicated by x, variable x. X stands for the distance from the illuminated spot to point A. How fast is that spot moving on the shoreline when it's exactly 6 kilometers from A? Well, what I'm asking you here basically is how fast is x changing over time when x is exactly 6 kilometers right here from point A. What is this? What is this? Okay, that's what I'm asking you. Now, this is not an easy problem, because not only do you have to interpret that, that's the first initial thing, is how do you interpret that in calculus notation, but then how do you solve it? I mean, because in these problems they don't show or tell you what equations to use, and that's the tough part for a student, is to figure out what in the world there is to use. Not only that, how do you interpret the given? Because we got the illuminated spot is moving along the shoreline. The angle theta here between the perpendicular segment 3 and the hypotenuse, which is the distance from the lighthouse to the illuminated spot. How fast is all this changing? Okay, so what relates x, which is opposite of theta, what relates that side, x, the adjacent side 3, and theta? What relates all 3 of those? You got to be thinking what in geometry or what in pre-calculus relates those 3 variables. Theta, which represents the change in the angle, okay, over time, or how fast the light is rotating in a circle, What relates that, the distance x, and 3, all at the same time. All right, so before we get that, let's go ahead and write down some given information here. A lighthouse is located on Thailand Island 3 kilometers from point A. Okay, the lighthouse lamp rotates at 5 revolutions per minute. This right here is the change in theta, okay, over time. That's equal to d theta dt, and that's going to be equal to 5 revolutions, all right, it says per minute. So I'm given that d theta dt, which is how fast this thing's rotating around, okay, because remember it's a lighthouse, because the light goes all the way around. Its speed or rate is 5 revolutions per minute. That in itself takes, some getting used to, and you have to interpret that. And not only that, you got to figure out, do I use revolutions per minute, or do I use degrees per minute, or radians per minute? Well, that all depends on the equation that you use. So let's go back to that. On this right triangle right here, what relates to the opposite side, the adjacent side, and the angle? And the answer to that question is the tangent function. We know that from basic geometry, SOHCAHTOA here, SOHCAHTOA, that the sine function, the tangent function relates to the opposite side and the adjacent side. So what I could do is I can set up the tangent function to help me out. So I know that the tangent of theta is equal to x divided by 3. All right, opposite divided by adjacent. That relates all 3 unknowns. And that in itself is the primary equation here. See, that's what makes related problems pretty challenging, is because in the problem it doesn't tell you how they're related. It doesn't tell you which equation to use. You have to figure that using a little creativity and all the basic mathematics that you learned in the past. Okay, that's why these are challenging. Not only that, you have to also recall that when you're dealing with trig functions, you want to be in radian mode. Okay, and because of this, let's make sure that we always remember be in radian mode, okay, when using all trig functions. When using trig functions here. So the question is, 5 revolutions per minute is how many radians per minute? We got to figure that out. Well, that's pretty easy to do. We're going to multiply it, all right, by a unit conversion factor. We know that there are 2 pi radians for every 1 revolution. So 2 pi radians for every revolution, 1 full turn. Well, you guys have been in physics and chemistry. You guys know that units cancel out nicely. Revolutions, or they call that dimensional analysis or unit conversion here. The revolution divided by revolution, they cancel out, and you get radians per minute. So what is 5 revolutions per minute actually equivalent to? Well, 5 times 2 pi is 10 pi, and we get radians per minute. It's over 30 radians per minute, guys. And that right there is the change in radius, the change in theta over time, which is how fast that light is traveling in a circular motion. Okay? So remember that. So that's all given here. I've got the equation here. What I need to do is differentiate it in respect to time now. So I need to take the derivative in respect to time of the left side, which is tangent theta. And I need to take the derivative in respect to time of the right side, which is x thirds, okay, or 1/3 x. Okay, here we go. So this requires a chain rule. So the derivative of tangent is secant squared theta times the derivative of theta, the inside function, which we call d theta dt. Again, there's a chain rule here. Right there. So let me just make note of that. There's a chain rule happening here. Because remember, with theta is a function of time, and tangent is a function. So we have a function within a function, which we call composition. And as we talked about in former sections here, guys, any composition or derivative of composition requires the chain rule. Okay, so the derivative of tangent is secant squared theta times the derivative of theta in respect to the time. That's your derivative of the inside function, is equal to 1/3 times the derivative, again this is 1/3 now, times the derivative of x in respect to time. So that's 1/3 times dx dt. And what we need to do now is take a look at what we have and make some substitutions in here. So now, let's see. I need secant of theta. I need to, I'll tell you what I'm going to do is I'm going to isolate dx dt. So I'm trying to find dx dt when x is exactly 6. So I multiply both sides by 3. Okay, and I get, if I simplify this, I get dx dt, which is what I'm trying to solve for, is equal to 3 times secant square theta times d theta dt. Now I want to figure out this derivative when x is exactly 6. Okay, so I can put a 6 here. Now, again, I'm trying to figure that out when exactly 6. So when x is exactly 6, that means I can figure out secant squared. Let's put a 6 here, if I knew what secant theta was. Now secant theta, let's go over off to the side here. Alright, side work here. There's a couple different ways you can do this, and this is one way here. I need to know what secant theta is. Now secant theta is the reciprocal of cosine. So if I knew what cosine was, then I could figure out what secant is. So let me see, 1 divided by cosine theta. Let me see, if this is 3 and this is 6, I can use the Pythagorean theorem to figure out what the hypotenuse is, and then take a look at cosine there, or get secant from there. Or I could use an identity, or I know that secant squared theta equals 1 plus tangent squared theta. I could use a form or identity. In fact, since I know tangent theta, tangent theta is just 6/3. That'd be much easier. 6/3 or 2. So from the diagram, what I can do is I can substitute in here 3 times 1, the quantity, 1 plus tangent squared theta times d theta dt, and I could use my knowledge of tangent and make a substitution there. By looking at the diagram, I know that tan theta is 6/3 or 2. So I can substitute 2 in here and square it. That'll probably be the easiest approach. So I've got 3 times the quantity 1 plus 2 squared times d theta dt, which we know is 10 pi radians per second. That's going to be equal to the change in the distance, or change in x over time, which is how fast the illuminated spot is moving along the shoreline. So I got 4 plus 1, 5, times 3 is 15. 15 times 10 pi is 150 pi. Alright, we're talking about kilometers here. X is in kilometers because this is in kilometers. So x is in kilometers as well. So we're talking about kilometers per minute here. Not per second, but per minute, because my revolutions, or my rate of change in the illuminated spot, or excuse me, or how fast the lighthouse is rotating, is per minute here. So I've got kilometers per minute. And that's going to be my change in x over time, or how fast the spot is moving along the shoreline. So how fast the illuminated spot is changing, or is moving actually along the shoreline. Not changing, but moving along the shoreline. Okay? Now, there's another way to do that. I could use the triangle, and I could solve for the hypotenuse here by using the Pythagorean theorem. I can get cosine, and then I can get secant theta and substitute that in, and I can square it. But if I do that, I get the same result. It just so happens that looking at the diagram, tangent of theta is really easy to get, and I used a little unique identity from the past here and substitute it in to get my what I wanted, because I know what tangent theta is on the diagram. So I make a little substitution, substitute in tan theta, which is 2, square it, and so on. Okay? I suggest if I went a little bit too fast, go ahead and go through it again and take a look at it in detail. Okay? Here's another situation here dealing with how the sand falls into a conical shaped pile at the rate of 10 cubic feet per minute. All right, so let's draw a little picture here. It's a conical shaped pile. So let's see, let's draw a cone here. It's conical shaped. And you know, it's obviously inverted because it falls into a cone. And you know, the sand is, you know, going in through here, the sand is falling here, and it's dripping down, and it gets bigger and bigger and bigger. So what's changing in this? You know, how high is it? You know, what's the radius, and so on. So let's read the problem again. Sand falls into a cone-shaped pile. Okay, that is obviously here at a rate of 10 cubic feet per minute. Cubic feet. This right here can be described as a volume per minute. So when it's traveling or coming in at 10 cubic feet, that's feet cubed per minute, that actually represents a volume over time. So we can represent that as the VDT. So I'm given actually the change in volume over time is 10 cubic feet per minute. And it's coming into the cone like that, so it's a positive value. Okay, just look at the units. If it's say cubic feet, that's got to be volume. Okay, the radius of the pile's base is always half the altitude. So if this is altitude is height, by the way. That's a fancy word for height. All right, so if I label this R here, the radius. This is a radius, of course, and the altitude is here. Altitude, okay, or another word, height, of course. You don't want to get too fancy right there. It says the radius of the pile's base is always half the altitude. Well, I'm given that R is equal to half the altitude, or altitude divided by 2, or height divided by 2. Or you can say that 2 times R equals H, however you want to describe it. Okay? Just keep that in mind. So we have we know how the radius is changing with the height. The question is right here, how fast, or when the pile is exactly 5 feet deep, how fast, again, there we go, rate is the altitude, H in this case, is it increasing? So this portion right here, okay, we need to find how fast the altitude is increasing. Well, that's dH dt, how fast height is changing over time when the pile is exactly 5 feet deep, okay, when H is exactly 5 feet. How fast is that? Okay, that's what we have to find. This question is how we're going to do it. All right, so we need an equation, obviously. All right, so what's our primary equation in the situation? Well, we need a volume equation for the cone. And again, that comes from geometry. So if you're thinking, hey, do you have to remember a lot of the geometry formulas? And the answer is yes. You know, and of course, you know, you can, when you're doing your homework and you don't know something, Google it, look in your geometry section, look in the calculus book. There's in the back or the front, I forget which, there's a resource center. Or you can go online. I mean, you can look at any resource you want. And then remember it, recall it, memorize it for the test. Okay? Got to do a little research if you forget what you learned a couple years ago. But if you forgot, let me tell you right now that the volume of a cone is related to the volume of a cylinder. And then the volume of a cone is 1/3 the volume of a cylinder. And this volume of a cylinder is just the area of the base times its height. And the cone is 1/3 of that. So the 1/3, the area of the base times the height. And this is the area of the base, which is a circle, and that's simply pi r squared. Okay, so what we want to do is simplify this a little bit. We're going to write the volume as 1/3 times pi r squared times the height. But notice that there's two variables here in this situation. And if I differentiate in respect to time right now, I'd have to use a product rule and the chain rule all in one. So to avoid that, what I'm going to do is I'm going to try to write the equation in terms of h only. Why h? Well, I want to figure out how fast the height is changing over time. Okay? To do that, I need an equation in terms of h only. Okay, so let's write this down. I want to write the equation in terms of, okay, h only. Because again, I want to find out how fast the height is changing over time. How fast is it increasing? So all I have to do is I have to take r, which is h divided by 2, and substitute in right here, in for r. Substitute it. Piece of cake. So what do we have? We have volume equals 1/3 times pi times r squared. Now r is h divided by 2. Got to square that, times h. And you want to simplify before you differentiate. Before differentiating. Differentiating. Okay? Why? Because it's a hell of a lot easier. Okay, so here we go. 1/3 or pi thirds. That's pi now. 1/3 times pi is pi thirds times h squared divided by 4. When you square a fraction, you square both numerator and denominator, times h. What do you get? You get pi thirds times h cubed divided by 4. Well, let's simplify even further. You get pi 12 times h cubed. And there's your volume. Pretty simple equation, actually. And now what you want to do is differentiate in respect to time. This is what you want. Differentiate in respect to time. Okay? I'm talking ddt here. So here we go. I want to differentiate the volume in respect to time, and I get dv dt. And then I differentiate this, and I get pi 12 times the derivative of h cubed, and that's 3h squared, times the derivative of h, the inside function in respect to time, and that's dh dt. Alright, now before we do anything, let's just go ahead and simplify a little bit. 3/12 is 1/4, and so I get the change in volume over time is going to be pi 4 times h squared dh dt. So let's go back and let's figure out what we want to find here. I want to figure out how fast is the altitude increasing. What's the change in height over time when h is exactly 5? Okay. So what I want to do, and then what's the change in volume? Let me see. The volume's coming in at 10 cubic feet per minute. Okay, so I better write this stuff over here. So dv dt is 10 cubic feet per minute. I want to find dh dt when h is exactly 5 feet. You know, what is that? So I got to substitute 5 in for h and 10 in for dv dt. So this right here is 10. We get equal to pi 4 times h, which is 5 squared, times dh dt. And I should get how fast the height's increasing over time in terms of feet per minute. Okay, not cubic feet, because we're not talking volume here. I'm just talking about h right here. Okay, so what is that? Let me see. We got 10 equals pi 4, or 25 pi actually. 25 pi 4 dh dt. And then of course I want to multiply by the reciprocal here. So that's, let me see, 4 divided by 25. Oops, come on. 25 pi on both sides, so multiply this. 4 divided by 25, come on, pi. And let me see, what do I get? 10 25ths is 2, 2/5 here, times 4 is 8. So 8 divided by 5 pi. 8 divided by 5 pi centimeters, no, excuse me, feet. We're not centimeters, that was the last problem here. Feet per minute, okay, equals the change in the height over time. And again, that's a positive value, so therefore it's increasing. It's an increasing rate. So an increasing rate because it's positive. Because it is positive. Okay? That's how fast the rate of, or the height is changing as the sand is coming in at 10 cubic feet per minute and when the height is exactly 5 feet above its base. Okay? Now once again, this is a video here, guys. You can run through it again. You can, I would suggest practicing the problem on your own. Try to do it on your own here, because the problems in your homework are going to be very similar in structure. You're going to have to interpret the problem, write down what's given. You're going to have to draw a diagram. You're going to have to write some equations, maybe some secondary equations like I wrote down, and a primary equation which you have to differentiate in respect to time. You might have to make some unique substitutions here, and then to solve for your unknown. All right, so give it a shot. Turn on the next page here and take a look at your homework problems here in this handout. So again, this is homework here. Go ahead and try these, and we'll check them. Check online, okay, and get help in class. Get help in class or in the intervention period. Intervention period. Okay, or go into lunch, do whatever it takes. Form some study groups, work with other people, and again, always write out what you're given, what you have to find, okay, what equation applies, and then go ahead and differentiate it and solve for the unknown. And if there's a diagram involved, draw the diagram, okay? If there is, draw one. So go ahead and go for it. I'll see you in class.